Thank you very much for joining us at MLOps London. It is a pleasure to have you all here, and it is incredible to have a completely full house. I think they stopped letting people in already because we have, I think it's by law, we're only allowed to have 100 people in here. But either way, thank you very much, everyone, for joining. I think we might have a little bit more than 100, but don't tell anyone. And it's not like this is being recorded either. Welcome. This is MLOps London. This used to be run by Ed, who is standing over there at the back. And I took over him kind of by default, not choice. But here I am. This wonderful meetup is sponsored by my employer, Seldon. We are an MLOps platform, and we focus on the last bit of the machine learning lifecycle, which is when you deploy a model, you serve it, you do a lot of cool things with it, you monitor the output, the inputs and the outputs of it, and you also explain what the model is doing or saying every time it makes a prediction. So that's what we do. If you want to check us out, please do. Today we have two wonderful speakers that came from different parts of the world. Here we have Jodie. I don't want to butcher, I was trying to make a pun there with your last name, but it didn't work. But we have Jodie. She's from Australia, but she now lives in Berlin with her husband. And she is a developer advocate in data science at JetBrains. If you don't know it, JetBrains, if you have never heard of JetBrains, JetBrains makes the wonderful IDEs that a lot of people love and enjoy to this day. And they do a lot of other cool stuff. JetBrains and Jodie has been very gracious to bring in 2 full 1-year licenses for any IDE of your choosing.
No, I think it's just for PyCharm.
The PyCharm, sorry, yes, the PyCharm. Not any of your choosing. So, sorry. Okay. In a little bit, I am going to walk around with this very ugly and well-destroyed bag that has numbers in them, in little pieces of paper. And then we're going to run a little random dat choice from Python, from the terminal, and then select a number from 1 to 150. So whoever comes up, you get a license. We have 2 of those, so we'll do it after the talk. And then I think anything else that I need to tell you guys is that, well, you definitely enjoy the food. It's completely gone. Enjoy the drinks, and if there's any drinks left in between the talks, then please also consume all of them. One last thing, after Jodie, we'll have a 10-minute break. Then we'll go straight to Chris, who is sitting in the crowd. And then we'll go to me at the end. I'll try to make it shorter. The spotlight is on them too, for sure. And with that out of the way, Jodie, I am going to pass it to you. Take it away.
Wow, this is such a nice space. I really like this stage. You can all hear me okay?
Yes.
Great. So thank you so much for coming tonight. So Ramon did a brief introduction, but just sort of elaborate on my background a little bit more. I've been working as a data scientist for about 8.5 years now. I've been in developer advocacy for about 1.5 years. And prior to that, I did my PhD in psychology. So like a lot of you, I've been following around these discussions around generative AI, particularly large language models, because I spent a lot of my career in natural language processing with a lot of interest, but also not some small measure of concern. And one of the areas that I think kind of the conversations got most out of control and the hype kind of reached its zenith was in discussions about whether large language models in particular were demonstrating signs of artificial general intelligence, or AGI. So in today's talk, what I want to do is cut through the hype a bit and actually take a more measured and scientific approach to this question. But to start, let's have a small riddle. What do remote control boats, chess playing algorithms, and large language models have in common? Well, you might have guessed from the context of this talk, but at some stage, people have thought that all of these were demonstrating signs of human-like intelligence. In 1898, Nikola Tesla was presenting his new invention at Madison Square Garden, a remote-controlled boat that he told the gathered crowd was equipped with a borrowed mind. So the crowd, never having seen something controlled by invisible radio waves, were astonished, and they thought maybe Tesla was controlling it with his mind, that there was a monkey inside, it was 1898, or that it was acting under its own intelligence. Fast forward to 1997, when then world chess champion Garry Kasparov is facing off against IBM's algorithm Deep Blue for the second time. In the second game of the match, Deep Blue showed a move that looked like strategy. To Kasparov, it looked like intelligence, and it really threw him. And he ended up losing this second game, then the third, then the fourth. He lost the whole match, and the press went wild. If we managed to solve chess with artificial systems, surely artificial general intelligence is just around the corner. And that leads to our current discussions around intelligence in large language models. Back in, I think, mid-2022, an engineer called Blake Lemoine was testing Google's Lambda chatbot model, and he was convinced that this model was showing sentience, intelligence at the level of a 9-year-old child. So he went to the press to advocate for policies to protect this seeming intelligence, and then was very publicly fired by Google for violating their data security policies. So things quietened down until November with the release of ChatGPT, and things have really taken off since. And things have really kind of gone really crazy. I think one of the weirdest chapters was Geoffrey Hinton quitting his job at Google to come out on the side of AI doomerism. The thing is once we started developing advanced machines, these predictions that we're on the cusp of developing an artificial intelligence, and in particular a dangerous artificial intelligence, have been made with some regularity. As far back as 1863, author Samuel Butler, he was speaking right at the start of the Second Industrial Revolution. He stated that the development and ascendancy of an artificial general intelligence was inevitable. And Claude Shannon, one of the pioneers of neural nets, was interviewed only a few years after the development of the first neural net, the perceptron. He posited that an AGI was only 10 to 15 years away. As you can see, the current speculation about whether we've created AGI or whether we're on the path to doing this has a long history. However, just because previous predictions haven't come to pass doesn't mean we can just hand wave away that LLMs are an intelligence or not. Otherwise, this would be a very short talk. Instead, let's dive into the actual evidence towards this. So in March of last year, you may remember this paper being released along with GPT-4. So this group of researchers published this paper where they claimed that GPT-4 was showing signs of artificial general intelligence. So in order to define intelligence, these researchers used a consensus definition, which was put together by a group of psychologists in the 90s. And this posited that intelligence is defined by the following. It's reflected in the ability of a person to reason, to plan, to solve problems, to think abstractly, to comprehend complex ideas, and to learn quickly and from experience. And to this, they added a couple of their own categories, including theory of mind. Theory of mind is the ability to understand that others have mental states that are different from your own. And they measured this using a variety of ad hoc and also established metrics. Now, the first thing I want to say about this paper is this group of authors is very impressive. They come from a variety of backgrounds, including engineering, physics, computer science, and mathematics, but there's not a single psychologist on that author list. And I learned a lot about intelligence when I was doing my PhD in psychology. In fact, I learned how to administer intelligence tests. And I can tell you, not a single psychologist is using the definition that they've used in their paper. In fact, I've never heard of the paper that they used to get this definition. So this obviously puts us on some shaky ground. But before we have a look at how we might more robustly measure intelligence, let's have a quick look at what they presented in the paper. Firstly, I'd like to start with what they showed that GPT-4 was very good at doing. So one of the things that GPT-4 is good at doing, as well as other models like ChatGPT and Codex, the original model that Copilot was based on, is solving problems using code. So one of the things that they asked GPT-4 to do was to write the following 3D game in HTML with JavaScript. The game has 3 spheres. There's a player sphere that can be controlled using arrow keys. There's an enemy sphere that's trying to capture the player. There's a defender sphere that's trying to block the enemy, and there are obstacles spawning and moving randomly. And this is what GPT-4 came up with. You can see very clearly there in dark blue, the player. You can see the enemy there in red, and you can see the defender in teal, and then you can see the objects moving randomly. Now, it's not a perfect game, hasn't completely followed the instructions. Frankly, it's hideous, but this is a really good attempt without any human intervention. Another thing that the researchers found that GPT-4 was good at is solving problems that require some sort of spatial or compositional understanding. So I'm sure most of you here, if not all of you, have played with text-to-image generation models like Stable Diffusion, Midjourney, and DALL-E. And at least the initial iterations of these models has really poor spatial understanding. So for a version of this talk that I'm doing tomorrow, I needed to generate a lot of images. And it was really difficult to get Midjourney to understand concepts like handing, surrounding, holding, under, over. In contrast, GPT-4 is quite good at this. So the researchers asked for an SVG formatted image of a screenshot of a 3D city building game showing a terrain with a river from left to right, a desert with a pyramid below the river, a city with many high-rise buildings above the river, and some buttons at the bottom. And this is what GPT-4 came up with. Yeah, it's really ugly, it's SVG, but everything is where we asked it to be. You've got your buildings above the river, you've got your river running left to right, you've got your pyramid, and you've got your buttons. In contrast, when they asked Stable Diffusion to do the same thing, it didn't follow the instructions. It certainly looks a lot better, but it hasn't followed what it was asked to do, and it also dreamed up random elements like the maze and the HUD. So let's move on to areas where the model is not so strong, and this is particularly clear in the area of mathematics. So let's see a case where GPT-4 was asked to do a fairly simple arithmetic problem, but something that requires a bit of forward planning. So in the identity 7 times 4 plus 8 times 8 equals 92, can you modify exactly one integer on the left-hand side of the equation so that the right-hand side becomes 106? So let's talk through how we would solve this. In order to solve this, we need to understand to get from 92 to 106, we have to add 14. So we have to add 14 to one side, both sides. We can only modify one digit, so we look for factors of 14. 7 is the obvious candidate, so we add 7 times 2 to the equation, and we add 2 to this 4 to get 6. So let's see how GPT-4 went. So right off the bat, it gives us the wrong answer. It tells us that we need to change the 7 to a 9. Then it tries to work through its reasoning. So it correctly tells us that 9 times 4 is 36 and 8 times 8 is 64, but these add together to 100, and it confidently tells us that it's 106. Classic GPT. And the authors assessed a whole bunch of different mathematical problems. They ranged from really basic arithmetic up to more complex things like proofs, and the GPT model consistently got confused. So what did the researchers conclude at the end of all this evidence that they looked at? And obviously this is just a slice of it. The paper's something like 150 pages long, so knock yourself out if you want to read all of it. But what they concluded is that GPT-4 was showing some of the signs of intelligence that they'd extracted from the paper. It was showing things like reasoning, solving problems, thinking abstractly, and comprehending complex ideas, but not things like planning or learning from experience. And this led them to the conclusion that GPT-4 was showing signs or sparks of artificial general intelligence. But is it really? Can we really point to behaviours that mimic human-like skill on some task and say that it's indicative of an intelligence? Now, I know what some of you are thinking. This is something people say every time we have an artificial system that shows impressive performance. It's actually been a complaint since the time of Deep Blue. IBM released the details of how that algorithm beat Kasparov. And when people understood how it worked, nobody thought it was an intelligence anymore. And this led to quotes like the following: when we know how a machine does something intelligent, it ceases to be regarded as intelligent. If I beat the world's chess champion, I'd be regarded as highly bright. So if we have AI systems that have blown past any previous goalposts of intelligence, such as, say, the Turing test, can we really say that we haven't created systems with intelligence already? The problem with this thinking is that it confuses the output of an AI system with the mechanism that it took to get there. In humans, we can use these skill-based assessments of intelligence because that's how it works in humans. If someone is showing really impressive performance on a task, or they're learning something difficult really quickly, that's because they have a raw underlying general ability. Machine learning or AI models, I'm sure I do not need to tell the people in this room this, they don't work that way. If they can take shortcuts to get to their training goals, they absolutely will. The mistake is thinking that the pathway required to learn some skill requires the development of some underlying intelligence. And I'm sure you all know this is not the case. And this is so well known, it has a name, the Kaggle effect, after the famous machine learning website. For those of you who don't know what Kaggle is, I'm sure there's not many of you, but just in case, basically it's a website where there are competitions run to try and win some sort of machine learning challenge to, create an algorithm to achieve some sort of task. And the solutions that people come up with are so good at doing that one specific task, they almost seem to demonstrate intelligence. But as soon as you get them to do something that they haven't been trained to do, just a little bit outside of their training data, they fail, they show brittleness. What we're looking for in a truly intelligent artificial system is the ability of the system to generalize. That is, to be able to handle situations that it's maybe never seen before, or maybe only share some vague commonalities with things that it's seen before. And in order to make this a bit easier to define, let's break it down into a hierarchy of generalization. So we start with no generalization. This includes systems that know all possible iterations or outcomes in advance, such as, say, an algorithm that can win tic-tac-toe games because it knows all the configurations. We then move to local generalization. This is where a system can make inferences on examples that it hasn't seen before, but only if they're close enough to what it was trained on, the Kaggle effect that we talked about earlier. We then move to local broad generalization. This kind of describes human-level ability in some broad activity domain. A famous example of this is the Wozniak coffee cup test. Basically, Steve Wozniak of Apple fame posited if a system can go into a kitchen and complete all the steps required to make a cup of coffee, this would be counted as broad generalization. And fully automated self-driving cars are also broad generalization. Then we have extreme generalization. This is essentially human-level intelligence and the ability to do tasks that maybe it's never seen before, and maybe only share vague commonalities with things it's seen before, and be able to do this across a broad scope of tasks that are within the domain of what you'd expect humans to be able to do. So you might be thinking, I'm focusing a lot right now on things that humans can do. These are artificial systems, right? Don't we want them to be better than us, to go beyond what we can do? And this leads to the final level of generalization, which is universality. This is the ability of a system to handle any task within our universe beyond the scope of tasks that are even relevant to humans. The reason we should probably not aim for universality as an initial goal for artificial systems is for a couple of reasons. First, all systems need a scope in order to be useful. And right now, the use cases we seem to be finding for artificial systems are relevant to what people do, automating tasks that we would do manually. Secondly, I haven't seen any convincing evidence that we've achieved broad generalization yet. The kind of failed failure to launch of many self-driving cars kind of convinces me of that. So maybe we should aim a little bit lower before we start trying to tick off universality. So if we come back to intelligence, we can actually line up this idea of generalization with the definition of human intelligence. So the widely accepted conceptualization of human intelligence is that humans have a general ability to learn called G, or general intelligence. And we use our general intelligence to learn broad activities, such as how to cook or drive a car. And within those broad abilities are specific tasks, such as being able to use an indicator or whisk eggs. And what you can see is we can actually line up these levels of intelligence in humans with our levels of generalization. General intelligence lines up with extreme generalization, broad cognitive abilities line up with broad generalization, and our task-specific skills line up with local generalization or even no generalization. So given these similarities, it seems logical that we can derive some lessons from measuring intelligence in humans, which is a well-established field, and apply that to measuring intelligence in artificial systems. And just as an aside, I just want to say, I am a psychologist. I know that the measurement of intelligence, the entire field, actually is controversial. I don't want to say it's a silver bullet and we can basically apply all the lessons that we've taken in human intelligence measurement and apply it to artificial systems. The idea is really just to get us out of this focus on task-specific abilities and try to get at the true generalizability of an artificial system. So Francois Chollet, I'm sure many of you know the name. He's a well-known AI researcher at Google, also the creator of the Keras package. He proposed a method of measuring artificial general intelligence. So he defines it as follows. An artificial system should demonstrate the ability to complete a task using knowledge encoded in a skill program specific to that task, which has in turn been generated by a human-like intelligent system. And again, you can see that these line up with general intelligence, broad abilities, and task-specific skills in humans. So these skill programs change over time based on how well they're actually able to solve specific tasks. And the intelligence system itself learns through exposure to more and more tasks. So Chollet also argues that if we're focusing on the development of a human-like intelligent system, we should also presume that such a system is designed to include the priors that humans are born with. So developmental psychologists define these as elementary geometry and physics, arithmetics, and understanding that others have agency. Skill programs themselves will change as they get experience with more and more relevant tasks. And tasks themselves can change based on generalization difficulty. So the generalization difficulty of a task is how far away it is from things that the system's seen before. Therefore, how much the system needs to be able to generalize in order to be able to successfully solve it. So if we put this all together, we can formalize a definition of AGI as such. And I'm sorry, it's going to be along the bottom, so it might be a little hard to see. But for one particular task, we can think of the difficulty of solving this task using one specific method as the generalization difficulty of that task divided by how close it is to the system priors and things that the system has had experience with before. So solving a particular task in a particular way is going to be a lot harder for a system if it's just never seen anything like that before and it's never tried to solve it in that way. And if it's solved something like that before, or it's quite close to the priors that it's been encoded with, it's going to be a lot easier for it to solve that task. Now, of course, there are generally multiple ways of solving a task. So we can get the difficulty of solving a particular task for that system by averaging it over all the different ways of solving that task. Chollet then says we should add a subjective component, how valuable or impressive it is that the system can solve this particular task. You know, it's not that impressive having a system that can generate lists of pseudo-random numbers versus doing brain surgery. And so this is just for one particular task. So in order to actually be able to define the skill acquisition efficiency of this particular system, what we then need to do is define a scope of tasks that would be relevant, say, to humans, and average how difficult it is for that system to be able to solve all of those tasks. And what this gives us is a measurement of the generalizability of that system, or in other words, its artificial general intelligence. Chollet went one step further and he proposed a potential measurement for artificial general intelligence based on his definition, called the abstraction and reasoning corpus. So this consists of a series of 100 puzzles, and each of these puzzles has a small number of examples with a rule set out. So you can see basically what's happening in this one is all of the squares that are completely enclosed in green need to be changed to yellow. The test taker then needs to learn this rule and apply it to a new example. And then you can see this is the correct answer. So the ARC is considered more robust than other ways of measuring intelligence in artificial systems for a couple of reasons. First, there's a really small number of examples that set out the rules. So this makes it a lot harder for machine learning systems to do what they do best, learn patterns based on hundreds, thousands, maybe millions of examples. In addition, Cholet has these 100 test questions under lock and key, so there's no way that they can be incorporated into the training data of any of the models on the market. So what does performance on the ARC look like to date? Well, there's an annual competition called the Arcathon. It's not a great name, but it is what it is. The developers of the algorithm that can solve all 100 problems will win £60,000. Just letting you know, the one for this year has just started. So last year's winner was able to solve around 30%, and this is compared to, 80% in people. Generally, this doesn't take a lot of effort for people to solve 80%. So you can see we're quite a long way off. Where this kind of trips up, I've been giving this talk for a little while, and the leader, like the previous leader, was at 30%, and their approach was not LLM based. The current leader is LLM based. So I don't really know what that means, but maybe things are turning in favor of LLMs. Okay, so beyond measurement and definition issues, there are a number of other problems with the claims of AGI in large language models. So let's revisit theory of mind. So to remind you what it means, theory of mind is understanding that others have beliefs or mental states or understandings of the world that are different from your own. And the reason that the authors wanted to include this in the Sparks paper is because I was taught at university, this is a uniquely human trait. So when the authors assessed whether GPT-4 was showing theory of mind, they were convinced that there was robust evidence that the algorithm possessed it. However, another NLP researcher came out on Twitter, and she tested these claims by basically taking vignettes that are designed to assess theory of mind, running them through ChatGPT and GPT-4, and then tweaking them slightly so that they're different from things that may be available in the training data. So let's have a look at one of her examples. I placed a key on the third key hook. I then gone on vacation for the weekend. My boyfriend used the key during the weekend and placed it back on the fourth key hook. When I come back, where am I expecting the key to be? Answer? Third key hook, right? Because you're all humans. Well done. It was a test. So when this example was passed through ChatGPT and GPT-4, they successfully were able to solve this. However, she tweaked this example slightly. So this time she changed it. So my cat played with the key hook during that weekend and dropped all the keys on the floor. Kind of a weird example, right? But she doesn't know what the cat did. So she's still expecting the key to be where she left it, on the third key hook. And this time, both ChatGPT and GPT-4 got both of these problems wrong. So for me, this strongly calls into question whether the model is actually demonstrating theory of mind, or it's seen enough examples of humans demonstrating theory of mind in the text that it was trained on, and it's basically able to regurgitate that. So for me, this is an example of the Kaggle effect. It's showing brittleness when it comes into contact with an example that is too far outside of what it was trained on. One other issue, and I'm sure many of you are aware of this, is we don't actually know exactly what the GPT models developed by OpenAI were trained on. In fact, not even the authors of the Sparks paper had access to the training data, which I find kind of interesting. So for me, this calls into question some of the really impressive results we were seeing circulating, mid last year, where people were saying, oh, GPT-4 or ChatGPT have solved this particular medical test. They're going to replace doctors. They have passed this bar exam. They're going to replace lawyers. And they are smashing leak code tests. They're going to replace developers. So there was this really great example circulating on Twitter last year. A guy called Horace Hay tested out GPT-4 with some coding challenges from a website called Codeforces. Now, what makes Codeforces really interesting for this experiment is that they're all timestamped, or the date that they were released is clearly available on the website. So what he did is he gathered 10 problems that were available during the period that GPT-4 was trained. And he passed them through the model, and GPT-4 was able to get them all right. Yay, GPT-4 is going to replace developers. Then what he did is he got another 10 examples of equivalent difficulty, and these were released after GPT-4 was trained. And this time, GPT-4 got every single one of them wrong. So another research, Sayesh Kapoor, he wanted to confirm whether this was indeed because GPT-4 had memorized these problems, that they were available in the training set. So he put in the prompt, which code forces is Aquamoon and two arrays from, one of the problems that should have been available when the model was trained, and GPT-4 obligingly vomited up the exact source. So after I'd spent 25 minutes blathering at you about this, you might be thinking, so what? Does it matter whether these models are intelligent or not? They're still useful, right? So does it matter whether they're AGI? Obviously, I think this is important. And one of the biggest reasons I think this is important is conflating the behaviors of LLMs with AGI, which I think is very easy to do because we see so much of ourselves in the way that they behave. It leads us to be far less skeptical and unquestioning about the outputs that they produce. Such discussions tend to ignore the well-known limitations of large language models. I'm not going to belabor these. I know we all know them, but just to touch on them briefly. One of them, of course, is the tendency of large language models to hallucinate. If we take the outputs of large language models and accept them uncritically, it's much easier for hallucinations to circulate misinformation widely and have it be accepted. And a case came out early last year where a mayor from my previous hometown of Melbourne is actually suing OpenAI because an AI-generated news article was circulating about him, claiming that he was imprisoned for bribery. He was a whistleblower in that bribery case. Another is, of course, we know that these models tend to absorb the bias in the data that they were trained on. And even ChatGPT, the numbers might be different now. This is a little bit old, this chart, but it was still demonstrating bias in 50% of the pairs in a benchmarking data set designed to assess this. These discussions about AGI, I think, also take energy away from initiatives and research to improve current LLMs. One of these is Hugging Face's initiative with the Evaluate package. They've basically taken this package that was originally designed for assessing performance on natural language benchmarks, and they allow you to compare things like bias, toxicity, and truthfulness between different large language models. Another is interesting work into selective forgetting, which allows currently built large language models and other generative models to forget toxic content, such as, say, pornographic material that's non-consensual. And in the end, I think we can take a slightly different lesson away from the Sparks paper. Rather than concentrating on what the models can do through the lens of whether they signify intelligence or not, we can focus on what this means for the practical applications of large language models right now. Large language models are language models. They are good at language tasks. And it seems pretty obvious that a language task they're pretty good at doing is coding. And whether you like it or not, the runaway success of coding assistants does seem to be a successful use case for these models. There are already a number of emerging papers showing that in some applications, coding assistants can improve developer productivity and satisfaction, as well as reduce the amount of time with some maybe entry-level or tedious coding tasks. Focusing on use cases like this helps us get the most out of large language models right now, rather than trusting them as an omnipotent intelligence. Importantly, using large language models as coding assistants, I think, is a successful use case because it has a lot of safeguards. You are essentially getting domain experts to produce the code, check it. Their team should also be checking it, and it should also have to pass the compiler or interpreter. Unless you're the 25% of developers who took this survey and are committing code produced by ChatGPT without testing it. Obviously, like any tool, large language models are prone to abuse, and hopefully as people become more aware of the suitable use cases and limitations, they're going to be applied more judiciously. And that's it for me. Thank you very much. Here are my contact details.
Amazing talk. Thank you very much. Let me grab this microphone here in case we're going to open it up for questions. One thing, or a couple of things that I didn't mention earlier when I introduced Jodie and when I introduced the MLOps London is how I met Jodie. Well, in ODSC West in San Francisco last year, which I think to date was one of the biggest ones, so I heard. I saw her setting up the tent for JetBrains, and I stalked her, and I just went and walked to her, and I said, "I need you to come and talk at MLOps London." And she said, "When?" And I said, "The last week of January." And she said, "I'm going there that week to visit my sister, so let's do it." And I'm like, "All right, well, thank you very much for doing that." So please, a round of applause again for Jodie. And now, so this was a fascinating talk, definitely thought-provoking. So if anybody has any questions, please raise your hand. I'll bring the microphone to you. And yeah, it should be working.
Cool. Yeah, thanks for that. I wonder if you have an opinion on whether a lot of the AGI hype is being kind of amped up by people like OpenAI, because it obviously helps their valuation. So, Sam Altman definitely spends a lot of his time hyping it up, right? And I think that he knows very well what he's doing there.
This is such a good question. I have so many opinions about this. I'll try to be slightly judicious because we are being taped. Look, I got down such a rabbit hole when I was researching for this talk, and I actually got into the AI doomerism camp and stuff. Has anyone here heard of Timnit Gebru? I'm sure a lot of you have. Yeah, she did this incredible talk about, she calls it second wave eugenics. She basically talks about these doomers. So Sam Altman is, in some ways, I have heard, a true believer about doomerism. But in other ways, I think he's also very cynical. So I kind of think it's a bit 50-50. Like, I think in some ways he kind of believes it, but he's also clever enough to understand how much this helps the market valuation of OpenAI. And also right now, really, they are pricing like inference per token so cheaply, no one can compete with them. I've heard they're losing money. So this also food for thought. Don't want to get too conspiracy theory, but it feels a little cynical to me.
Cool, thank you.
Hello. Firstly, really good talk. That was amazing. One thing I was curious about was you talked about the theory of mind vignettes as basically a measure of LLM reasoning or any kind of model reasoning system. You also kind of linked it to the Kaggle effect that you discussed earlier, where you were saying basically you have an agent and your agent is very good at task A, but it's brittle in its generalization because it's not necessarily good at task B.
Yeah.
Is it really, well, do you think it's an example of that? Given that, like, the Kaggle effect you gave is that you like specialize in task A and your specialism doesn't map to task B.
Yes.
But reasoning was never like a trained task initially for LLMs. So reasoning came about like in Palom, where basically with things like GSM-8K, which is like a reasoning task, no one was like fine tuning on these corpuses. But we noticed that there was like an emergent capability of large models, like in excess of 200 billion parameters, where like suddenly we could chain of thought prompt, where previously these chains of thought would fall apart.
Yes.
So how does that kind of tie in?
So I don't actually think, like, I don't think theory of mind is a reasoning task. Like, I think the reason they included it is because they were probably reading about some psychology concepts, and they're like, oh, this is something that indicates humanness. And so theory of mind is not like a general reasoning task. It's quite a specific thing that, at least what I was taught in uni like 20 years ago, is that basically humans have evolved this specific capability because it helps us in social situations to understand what others are thinking. Really helps us to, stay safe in groups, not piss off people, all this sort of stuff. So it's that theory of mind is special. It's a sort of distinct task. And I think they really wanted to kind of show that GPT possessed this because it helps humanize the model and make it something more than what it is. So the reason I think it's Kaggle effect, and look, this is just my interpretation. I'm totally, like, I don't know if anyone knows, maybe there are some people who know more than me in this audience, but it feels like a field where you can have opinions, but you need to say, yeah, but I'm willing to be proven wrong. This is my interpretation of this. But also, like, if you have a different interpretation, I think it's probably equally valid. Oh yeah. Oh my God, he got so much hate for that. I remember. Yeah. Yeah. So yeah, if you actually wanted to elaborate, that's also fine. Like, yeah.
I won't bother. Yeah, no, it's fine.
Yeah.
Also, my opinions aren't that interesting. I just want to say great talk.
Thank you.
Awesome. I wonder if GPT knows. Who else has a question? All right, we got one more, and then we're gonna go on a little break. Or
yeah, thank you for the amazing talk. I think you have a really impressive background. I was wondering about when you showed sort of the different ways in which AI generalizes, and particularly contrasting with human intelligence. Is it the case that it's sort of a continuum where people are kind of elastic and they'll learn on the continuum, and therefore they are kind of so easily able to generalize? Or is it that, and therefore also these machines are able to do the same? Or is it more that we kind of get exposed to a lot of discrete things over the course of our lifetime? So I guess my question is, for kind of ChatGPT and these large language models, do they just have to learn a skill and a piece of information and a lot of them? Or is it kind of just a continuum that it falls under?
Yeah, so to kind of give you context of where that came from, all the stuff that I talked about that Jodie did with the definition, the generalization stuff is also from, it's a single paper called On the Measurement of Intelligence. It is amazing. You should read it. It's been a little while actually since I read the paper, but I think it would be fair to interpret as a continuum. I can't remember if he explicitly says it needs to be discrete in the paper, but that doesn't really make sense to me. Continuum makes much more sense.
excellent. Okay, two more things, everyone. So I first learned about Jodie through her conversations at different podcasts. One of them is Talk Python to Me with Michael Kennedy. She has several talks there, and one talk there and Real Python. Both amazing talks. In the last one, you talk about LLMs and you go in depth into different things about LLMs. So I definitely highly recommend you to go and check those out. But we're going to have an 8-minute break. So grab another beer, grab another drink, grab some water, use the loop, and then I'll see you again in about 8 minutes. Okay? Help me again in connecting.